In this video, we begin to explore yet another distribution, namely the binomial distribution. To start with, the binomial distribution only applies to discrete random variables. In other words, it can only be used to model a random variable whose values are obtained from a counting operation. So, what are examples of real-life scenarios where the binomial distribution can apply? Let's take some examples of situations where it might apply versus ones where it will not apply. Here's an example of a scenario. If a hospital tracks the waiting times of patients in emergency department and wants to model the distribution of those times, can they use a binomial distribution? No. The reason is that the variable of interest, the waiting times of patients, this is a measured quantity in the real world. And so, in this case, this will constitute a continuous random variable. The binomial distribution does not apply to continuous random variables. Rather, it applies to discrete random variables. So in that case, or in this scenario, the binomial distribution will not apply. Let me jump to part C, and then I'll circle back to part B. If we're told to find the probability of obtaining 8 heads in the toss of a coin 3 times, I'm going to use this example to show that the binomial distribution applies in solving this problem. How? I would show using this illustration that it meets at least the first 4 critical criteria. And let us see what that is. You see, if you consider what this problem requires, which is to find the probability of obtaining 8 heads in the toss of a coin 10 times, you will notice that this toss of a coin, this is a trial. The trial to observe an outcome. How many times was it carried out? Was it carried out a particular definite number of times? Yes, that is 10 times. So your n in this case, the fixed number of trials, keyword fixed or definite finite number of trials, n is equal to 10. So it meets the first criteria for a scenario that can be described by a binomial distribution. Then the next one is in the toss of a coin, which represents a trial. Does it only have 2 possible outcomes? Yes. The possible outcomes here are head or tail. So it meets this condition too. Then for this scenario, the outcome of tossing a coin once, does it dictate the outcome of the next toss of the coin? No. That is, the trials, the toss of the coin, the outcomes observed on each are independent of each other. So again, that condition is met. Then what else do we need? The process must be consistent in generating successes and what failures. In other words, the probability of success must remain constant from trial to trial. If you toss the coin the first time, the probability of getting a head is 50-50. If you toss it the second time, the probability of a head is still 50-50. The probability of getting whatever you're interested in, which is the head in this case, would be 50-50 or 0.5. So, since all of these conditions are met, this scenario can be solved using the binomial distribution or can be described using the binomial distribution. Let me draw another contrast to B. We want to look at the probability of picking 2 blue balls without replacement from a bag having 3 blue balls, so blue, 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 and 4 white balls, white, 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 white. Okay, notice where the problem arises. It is the fact that we're picking the balls without replacement. How? The first time you pick a blue ball, and we're interested in the blue balls, right? Good. If you're going to pick a blue ball, we stand 3 out of 7 chance of selecting a blue ball the first time. Then the second time, after the first blue ball has been picked, remember the first blue ball will not be replaced. So picking a second blue ball will be out of 6 because you're not replacing the first blue ball. And then this will be 2 over 6. What do you notice? Even though we're interested in the probability of picking 2 blue balls, the first probability of picking a blue ball of the first blue ball was 3 over 7. However, the probability of picking a blue ball after the first blue ball has been picked without being replaced is 2 out of 6, which means that we have violated rule number 4 for a binomial distribution. The probability was supposed to remain constant from one peak of a blue ball to another, which is a trial to trial. That condition is not satisfied here, since 3 over 7 is not equal to 2 over 6. So we cannot model scenario B with a binomial distribution. Having noted what makes a binomial distribution useful and how it can be characterized, let us see how we can compute probabilities associated with a binomial distribution. So take note, for a binomial distribution, there are two key parameters. One, the fixed number of trials, which is 10, and then two, the probability of success, which must remain constant from one trial to another. That value must remain constant. As in the case of toss of a coin, if we're interested in heads, we want it to be either 50-50 from one toss to another. Now, once we identify a binomial scenario, it can be described using a binomial distribution, and it has a formula for computing probabilities, which we won't get into. But take note that if you try an experiment 6 times, this n represents the number of trials. If we try it 6 times, and x is the number of times you have an outcome that you desire. So take note that in 6 tosses of a coin, x, the number of successes could be 0 success, 1, 2, 3, 4, 5, or 6 successes. And for each of these possible successes, there's a likelihood they will occur. So there's a probability that you will get what? 0 success, a probability that you get 1 success, probability that you get 2 successes, 3 success, 4, 5, or 6 successes out of 6. In particular, this question is asking us what is the probability that you get 2 successes? The formula, as long as the binomial distribution applies, is n combination x times p raised to power x 1 minus p n minus x, where in this case our n is the number of trials, so I'm going to replace that with 6. My x is equal to 2 for this question, and my probability of success is 0.08, so 0.08 raised to power what? Raised to power x. Our x is 2. And again, you have 1 minus 0.08 raised to power n minus x. Our n is the number of trials, 6 minus 2. To evaluate this, we're going to deploy the computing strength of StatCrunch. So let me do that. So I'll StatCrunch here. I'm going to close out of the normal distribution, go to Stats, go to Calculators, go to Binomial, and from the dialog box that pops up, let us drag this up. The number of trials is 6. The probability of success is 0.08. And I would like to find the probability that is amassed at the point 2. So let me say at the point 2, and I can compute that. So that will give me the value of this computation. So in which case I have 0.0688. Done. Again, for the next question, I am to find out of n equals our number of trials is 9. So my number of successes out of what? These trials could go from no success, 1, 2, as far as 9. But in particular, I am interested in the collection of all possible the probabilities for all values of x below 4. So that will be for x less than 4, that begins from 3. I'm interested in the amount of probability collectively at all values below 4. So what I will do is go to StatCrunch. My number of trials is 9. My probability of success is 0.80. And I'm interested in less than strictly less than 4. And I can compute that. And that would give me 0.0031. Next, I have what? My n is equal to 11, and my probability of success is 0.65, and I'm interested in a between case. All right, take note that this is equal to, which means that the endpoints must be included. So we need to do a little bit of brain work here. And what brain work is that? Let us see. If our n is 11, my x, the number of successes can go from as low as 0, 1, 2 to, if I'm having a very good day, for 11 trials, I am making all 11 what? Successes. So it can go as far as 11. Now I'm interested in a couple of things. Probabilities at certain areas between 2 and 6. Between 2 and 6, that will cover the probability at 3, 4, and 5. Then this equal to means I should also include the probability at 6. But since there is no equal to pointing to 2, I cannot include that of 2. So I only want the probability from 2 to 6 inclusive, from 3 to 6 inclusive. So I am going to say from 3 to 6 inclusive. Remember, 3 is taken out. So compute, and you have equals 0.3297. The next one is to find the case where our n this time is 14. Number of successes can go from 0, 1, 2 up to 14. Well, just before 14, there is what? There is 13. And I'm interested in the probability at equal to 13 and above. Well, above will only go as far as 14. So in this case, I can use StatCrunch 2 to help me get to that value to collect the total mass of probability here. So this time I'll go back to standard. I'll switch back to standard, and I want what? 14. Probability is 0.95, and I want greater than or equal to 13. And let's compute that. So that gives us 0.8470. And finally, I have another one here where the number of trials was 20. Our x is 0, 1, 2, 3, 4, as far as 20. And I'm interested in the probability that the number of successes is greater than 3. So that will start from where x is greater than 3, 4, 5, up to what? 20. So that's from 4 to 20 inclusive. So I can go back here put greater than, and then I have what, 3. Uh, Let me change this to 20, and the parameters 0.50, and greater than 3, compute. So I have the total probability from 4 to 20 is 0.9987, very close to 1. So 0.9987. Let us see another example. Talking about the mean and the standard deviation of a binomial random variable. The mean of a binomial random variable is n times p, the number of trials times the probability of success in each trial, and the standard deviation of a binomial random variable, the standard deviation, short for SD, is the square root. That is the square root of np 1 minus p. Let's take an example here. So in this case, according to a Gallup poll, 60% of American adults prefer saving to spending. Let X be the number of American adults out of a random sample of 50 who prefer saving to spending. Calculate the mean and the standard deviation. In this case, in this scenario, we have what? A binomial distribution, because 1, we have a fixed number of people we are trying to see if they prefer saving to spending. So our n in this case, the probability, the number of people we are trying is 50, whereas p, the other parameter of the binomial distribution, is 60% here, because historically, every next person we see here, the probability that they will prefer saving to spending based on past data is 60%. And to calculate the mean, so our x in this case follows what? The binomial distribution, where your x is the number out of 50 who prefer saving to spending. And that would be n equals what? 50, and p equals 0.60. And so we want to find the mean of the random variable x. That will be the expected value of x, or mu, which is n times p. That will be 50 times 0.60, which is 30. Then we look at the standard deviation. The standard deviation of our binomial random variable, and that will be the square root of np 1 minus p. We got an answer for n times p earlier. That was 30. So you have 30. Then you have 1 minus p. P is 0.60. And so eventually, this is equal to 30 times 0.40, which is 12. And that will be approximately 3.46. All right, let's look at yet another example. A retail store pays the manager $500 bonus if the team gets at least 12 store credit signups in a day. From past data, each eligible checkout has a 15% chance of resulting in a sign-up, independently of others. On a typical day, there are 60 eligible checkouts. Question A. What's the probability that the manager earns the bonus? In this scenario, we have a binomial distribution. How do I know that? Well, we're interested in particular in the number of store credit signups. So I'm going to let x, my random variable of interest, be the number of the number of store credit signups, and out of how many people on a typical day there are 60 eligible checkouts. So with that said, my x follows a binomial distribution with n equals 60 people to be tried to see if they will sign up or not, and with a probability of 15%, because there's a 15% chance that results in what? A sign up, and it's independent of others. So in this case, take note that the binomial distribution criteria is met because either a person will sign up or not. So you have two possible trials for each trial, and there is a fixed number of what? There's a fixed number of people we're trying. The probability of success remain constant from trial to trial, and there is the independence of outcomes on each trial. So now we want to find the probability that the number of what? Of earning the bonus. That is what the question says. And that bonus is a $500 what bonus, okay? But that only happens if the number of what? Credit signups is at least 12. So that is the probability that X, the number of signups, is at least 12. At least 12 then would mean I need to compute the probability that X is greater than or equal to 12. So let's go back to our calculator. And I want to go to the binomial distribution. So I'm going to key in the parameters of this distribution. You have 60, and then you have 0.15, and we want the probability of greater than or equal to 12. Compute. At this point, do note that when you're dealing with a discrete distribution, greater than or equal to is not the same as greater than, which is why you have different options for this. All right, so you have 0.1806. So this is 0.1806. With that said, let us look at the second part of the question. We are to report the expected number of signups. So part B, this is part A, 1. Expected number of X, because X is the number of signups. Since we're dealing with a binomial distribution, we're good to use this formula only when we're dealing with the binomial distribution. So that would be 60 multiplied by 0.15. And using my calculator, I have 9. This is the expected number of signups if what past data, the trends in the past data remains what? Applicable. Then B2, in this case, we're also to find the variability so that the management isn't getting in the dark. Measure of variability is the measure of spread. So that will be the standard deviation, which is the square root of NP times 1 minus P. So that will be the square root of 9, 1 minus 0.15. So 9 times 0.1 times 1 minus 0.15, that will be 0.85. So you have the square root of 7.65. So taking the square root of 7.65, we have 2.766. That completes that part of the question, or that question.